For this week's interactive advanced concept presentation, we had the opportunity to learn about how nuclear bombs work. I will first discuss the type of nuclear chemistry needed for a nuclear bomb to work and what is occurring inside this reaction. The isotopes uranium-235 and plutonium-239 were selected by the atomic scientists because they readily undergo fission. Fission occurs when a neutron strikes the nucleus of either isotope, splitting the nucleus into fragments and releasing a tremendous amount of energy. The fission process becomes self-sustaining as neutrons produced by the splitting of atoms strike nearby nuclei and produce more fission. This is known as a chain reaction and is what causes an atomic explosion. When a uranium-235 atom absorbs a neutron and fissions into two new atoms, it releases three new neutrons and some binding energy. Two neutrons do not continue the reaction because they are lost or absorbed by a uranium-238 atom. However, one neutron does collide with an atom of uranium-235, which then fissions and releases two new neutrons and some binding energy. Both of those neutrons collide with uranium-235 atoms, each of which fission and release between 1 and 3 atoms, and so on. This causes a nuclear chain reaction. I will discuss what components are necessary to achieve the chain reaction required for nuclear fission a little later. In order to detonate an atomic weapon, you need a critical mass of fissionable material. This means that you need enough U-235 or Pu-239 to ensure that neutrons released by fission will strike another nucleus, thus producing a chain reaction. The more fissionable material you have, the greater the odds that such an event will occur. Critical mass is defined as the amount of material at which a neutron produced by a fission process will, on average, create another fission event. I will now discuss what components are necessary to achieve the chain reaction required for nuclear fission. So nuclear fission is a type of nuclear reaction where two light nuclei collide together to form a single, heavier nucleus. Fusion results in a release of energy because the mass of the nucleus is less than the sum of the original masses. Based on the principle of the mass-energy equivalence, this mass difference means that some of the mass that was lost has been converted into energy. For elements lighter than iron, fusion often releases energy. For elements heavier than iron, it takes energy to cause fusion to happen. In order to make elements heavier than iron, either a high-energy particle beam is required or a supernova. Although the fusion of small atoms gives off a lot of energy, initiating this process requires a significant amount of energy. This energy is needed to overcome the Coulomb repulsion that exists between the protons and the two different nuclei. Hydrogen atoms must be pushed close enough together so that the strong nuclear force can overcome the Coulomb repulsion. The initial energy needed is a major factor which makes fusion difficult to achieve. There are several different types of reactions, but most involve two isotopes of hydrogen known as deuterium and tritium. Some fusion reactions include a proton-proton change. So this type of fusion reaction is the one that takes place in the sun. There are two pairs of protons, which are the two pairs of hydrogen atoms that collide and become two atoms of deuterium. Each deuterium then combines with a proton, hydrogen, to form helium-3, which combine again and eventually form helium-4. Deuterium-deuterium reactions is a pair of deuterium reactions combined to form helium-3 and a neutron. And the last type of reaction is a deuterium-tritium reaction. And for this to occur, one atom of deuterium combines with one atom of tritium to form helium-4 and a neutron. Currently, there are no large-scale fusion reactors that could provide energy for commercial use. This is because it has been difficult for scientists to create a controllable, non-destructive way of harnessing the energy released during fusion. This process of fusion is difficult to control largely because of the extreme conditions necessary for the reactions to take place. First, fusion requires both extremely high temperature. The high temperature gives hydrogen atoms enough energy to overcome the electrical repulsion between the protons. Fusion requires about 100 million Kelvin. At these temperatures, hydrogen is a plasma rather than a gas. Plasma is a high energy state of matter in which all electrons are stripped from atoms and move freely about, to give hydrogen atoms enough energy to overcome repulsion between the protons. Energy from microwaves or lasers must be used to heat hydrogen atoms to necessary temperatures. At these temperatures, hydrogen is a plasma, and this plasma must be sufficiently contained for fusion to continue in safety. Secondly, high pressures are needed to squeeze hydrogen atoms close enough to fuse. This process is done by using intense magnetic field, lasers, or ion beams. For potential nuclear energy sources, the deuterium-tritium fusion reaction is most likely because the conditions are less extreme. With current technology, we can only achieve the temperatures and pressures necessary to make deuterium-tritium fusion possible. Deuterium-tritium fusion requires higher temperatures that may be possible in the future. Ultimately, deuterium-deuterium fusion will be better because it is easier to extract deuterium from seawater than to make tritium from lithium, although deuterium is not radioactive and deuterium-deuterium reactions will yield more energy. Thank you.